Hello, my name is Justinas, and I will be presenting our work called Data Augmentation with Generative Adversarial Network for Solar Panel Segmentation from Remote Sensing Imagery. The usage of renewable energy is becoming more popular every year thanks to its increasing accessibility and affordability, especially for homeowners who install solar panels on the roofs of their houses. The use of remote sensing, including satellites and drones, helps observe the increase of solar panel usage in urban areas and the expansion of solar panel farms. Furthermore, it allows for better strategic planning for policymakers and development of electrical grid plans. To make the monitoring process more effective and less labor-intensive, semantic segmentation models are used for object labeling in remote sensing imagery. However, when training semantic segmentation models, two common problems arise: the image annotation process being time-consuming and labor-intensive, as well as the lack of data quantity and variety for specific tasks. For solar panel semantic segmentation model training, large amounts of data are needed for better model accuracy, and the scarcity of precise solar panel location data makes the manual labeling even more difficult. Furthermore, classic data augmentations, such as rotations, flips, color shifts of samples, etc., although they produce more samples, they are not unique data and limits the potential of semantic segmentation model training. Therefore, this study aims to leverage the Pix-to-Pix Generative Adversarial Network model for additional training sample generation from existing limited data and improve the solar panel detection accuracy of the DeepLab v3 semantic segmentation model. Transfer learning and fine-tuning techniques are also applied to the DeepLab model. Also, the issue of limited data is being addressed, avoiding the manual creation of new data and using the newly generated synthetic images as an alternative to classic augmentations. A collection of various remote sensing images and solar panel segmentation mask pairs was used for the training of both the semantic segmentation model and the generative adversarial network. These images are of various spatial resolutions as well as different sizes, and resampling was applied by either padding or cropping the images, depending on whether they are smaller or larger than the target size of 512 by 512. If they are smaller, padding is applied, and if they are larger, cropping in region of interest, i.e. the center of largest solar panel object in segmentation mask, is applied. After that, the images are resampled to 10 cm target spatial resolution. This is done to prevent as much information loss as possible and avoid scale discrepancies, as well as keep consistency during model training process. The Pix-to-Pix Generative Adversarial Network is trained using the same training data as for the DeepLab semantic segmentation model for the task of translating semantic segmentation masks input data to real remote sensing images, target data. In the process, the generator attempts to generate realistic images that are faithful to the target data, while the discriminator tries to tell apart real images from the fake ones. The discriminator losses are backpropagated to the discriminator, indicating how well this module can identify real or fake generated images. The generator L1 and GAN losses are backpropagated to the generator and signal the difference between the original and synthetic image, and how well the generator can fool the discriminator. This balance of power between the generator and discriminator are crucial for effective learning of the generative adversarial network. Because the new remote sensing images are generated from existing limited training data, the result is an additional 2048 pairs of new data that provide more variety compared to regular data augmentation applications. The top row is the original data, and the bottom row is the synthetic images. Note the differences in landscapes, such as building locations and shapes, road formations, as well as the solar panels themselves in some cases being generated a bit differently with different patterns, introducing more variety to data. However, once we have all the generated samples, the question arises, how many samples do we need? To determine the optimal GAN-generated data amount for training the semantic segmentation model, sensitivity analysis was performed, training the DeepLab model using transfer learning and incremental amounts of additional GAN-generated data. This method finds the optimal amount of generated synthetic data before the model is impacted negatively. Validation and testing subset intersect over union and loss metrics were compared, and the changes with additional GAN data usage was detailed in the figures. Because the criteria used for determining the best performing variation of the model was validation intersect over union in this case, 60% was selected as the best number of GAN-generated images to use for appending the original training data. Overall, 6 models were trained and tested, one without augmentations of any kind, one with classic augmentations, one with 25% of extra GAN data, then one with extra basic augmentations, and with the optimal amount of extra data, 60%, as well as basic augmentations. Compared to the baseline model, no augmentations, the model GAN optimal displayed improvements across all metrics. Based on the intersect over union metric, which is important in determining the percentage of correctly segmented solar panels, the 256 images in the testing subset were categorized by good segmentation, at least 50% of the solar panel found, poor segmentation, less than 50% of the solar panel found, and by no solar panels found. The model GAN optimal, trained with an additional optimal amount, 60% of GAN-generated data, also correctly segmented more solar panels in remote sensing images compared to the baseline model. Notably, the application of basic data augmentations for models trained with additional GAN data did not result in improvement of all metrics, likely indicating training challenges of augmented synthetic data. The improvements of the optimized model are also evident in tests with real-life data of various locations throughout Lithuania, including solar panel installations. The best results are of the GAN optimal model, with better solar panel recognition in terms of edge detection and overall object recognition. In conclusion, using the generative adversarial network is beneficial for training dataset augmentation with brand new remote sensing images from existing limited data, especially when the optimal amount of GAN-generated data is determined with a sensitivity analysis. Expanding a limited data set with newly generated pictures helps train the solar panel segmentation model for better accuracy and segmentation quality, compared to using classic data augmentations. Furthermore, having new images produced using the generative adversarial network eliminates the need for labor-intensive and time-consuming manual annotations for training data creation. The applicability of the research includes the possibility of a precise solar panel map creation, which in turn would be beneficial for market analysis, grid planning, and real estate risk evaluation. For future plans, cyclical generative adversarial model application for style transfer is considered. It can potentially introduce even more variety to training data, with the simulation of different weather conditions, such as snow, and landscapes in remote sensing images. The increased variety is expected to lead to semantic segmentation model increased accuracy and precision. Furthermore, hyperparameter tuning of the models, as well as a more precise sensitivity analysis with more runs to account for potential randomness, is planned, although with more computational resources. Thank you for your attention.